loop MNOP of side 20 centimeter is placed horizontally in a uniform magnetic field acting vertically downward as shown in figure. The loop is pulled with constant velocity of 20 centimeter per second till it goes out of the field. 1. Depict the direction of induced current in the loop as it goes out of the field. For how long will the current in the loop persist? 2. Plot a graph showing the variation of magnetic flux and induced EMF as a function of time. So we are asked to show the direction of induced current in the loop as it goes out of the field. And we know when the loop goes out of the field, okay, there is change in flux. So change in flux produces induced EMF and hence induced current. Okay, so we are asked to calculate how long will the induced current persist in the loop, and we are asked to plot the variation of magnetic flux and induced EMF as a function of time. Clear? Now we can see, okay, we have this diagram, okay, given. Now we can see in this diagram, okay, magnetic field. So let us denote magnetic field by the symbol vector B, okay. So this is magnetic field and it is perpendicular to the plane, okay. It is perpendicular to the plane of the board, okay, and is directed inward. So we have this, okay, magnetic field perpendicular to the plane of the board and is directed inward, and magnetic field is uniform. Now we can understand this situation or figure in this way also, okay. We have, let's say, X, Y and Z axis, okay. We have a square loop, okay. We have a square loop MNOP of side 20 centimeter. So what we find, okay, square loop is in horizontal plane XZ, okay. So we have this, and we have magnetic field acting vertically downward, okay. So we have magnetic field acting vertically downward. So we have this. So this is magnetic field acting vertically downward, that is along minus or negative Y axis. So we have this, okay. So we have this. This is negative Y axis, okay. So we have magnetic field acting vertically downward. So it means that magnetic field B, okay, is perpendicular to the plane of the loop. So we have this situation, okay. So we can understand in this way. Now, as the loop is pulled, okay, loop is pulled, okay, loop is pulled towards right side. So it is pulled towards this direction, okay. So let's say the loop is at this position, okay. So I'm indicating this phase as 1 and this phase as 2. So this is phase 1 and this is phase 2, okay. Now in these two position, okay, in these two position there is no change in flux. So from this edge to this edge there is no change in flux. Clear? So From this position to this position, okay, there is no induced EMF and hence induced current, okay, because there is no change in flux. Now, this position, okay, this position, so let me write in this way. From this position, if the loop is further pulled towards right side, okay, then the loop starts, okay, going out of the field, okay, it starts going out of the field, Now, when the loop, when the loop is just completely outside, okay, just completely outside the field, okay, just completely outside the field, then, okay, what we have, then we have phase 1. So this is phase 1 of the loop, will be at the edge, okay, edge. So this is the right edge, okay, right hand side edge, and this is the edge of field on left hand side, okay. One will be at the edge and phase 2 will be completely, okay, outside the field. So we have this situation, okay, we'll have this situation, we will have this situation, okay, we will have this situation, we'll have this situation, clear? This is phase 2 and this is now phase 1, clear? We'll have this situation. So we can understand further in this way also, okay? So we have this is phase 2 and this is phase 1. And when it is completely outside, okay, when it is completely outside, as I said earlier, okay, we get this situation just outside, okay, we have this. So this is phase 1, this is phase 2, and when we pull it further, okay, then we get this completely outside. Okay, this is completely outside. So we have this. Okay, so we have this. Now this is just completely outside. Outside the field, and in this diagram, okay, we have this situation. So it is the intermediate condition, okay. Some part of the loop, okay, some part of the loop is completely outside the field, and some part of the loop we can see, okay, some part of the loop is completely inside the field. So we have this situation. Clear? So we find this. Now let us come to this question once again, okay? We are asked to fix the direction of induced current in the loop as it goes outside, okay, the field. And we know when the loop is completely, when it is completely inside the field, okay, there is no change in flux, even though the loop is moving, okay? So I'm writing over here. When the loop is inside the field, okay? When the loop is inside the field, okay? Inside the field, there is no change in magnetic flux, okay? There is no change in magnetic flux, even though the loop is moving, even though the loop is moving. So induced EMF, okay, and hence induced current is zero, okay? It is zero inside the field. So we have this. Now, as the loop, okay, as the loop goes out, okay, it goes out of the field gradually because we are pulling it towards right side. So what we find, as the loop goes out, the area, okay, of the loop, clear, through which the magnetic lines, okay, are crossing, okay, decreases, or we can write in this way, is decreasing, okay? We can see what we find in this situation, okay? We find the area of the loop, okay, is maximum. So we find maximum magnetic lines crossing through this area. So as the loop is pulled out, okay, the area of the loop, okay, decreases. So we find only this area, okay, in this figure we find only this area, or only magnetic field lines is crossing through this area. So as it is pulled further, the area through which magnetic lines or magnetic flux is crossing decreases. And we know this, okay? Magnetic flux, we have this relation, okay? We know magnetic flux phi equals the dot product of magnetic field with area vector, okay? So we have this. Now, due to which, okay, due to which flux, okay, is decreasing. So we have this. Now, from Lane's law, okay, there is decrease in flux. So according to Lane's law, because we know whenever there is change in flux, whether flux is increasing or decreasing, okay, we need to have change in flux. So in this case, okay, we have decreasing flux means, okay, we have change in flux. So change in flux produces induced EMF and hence induced current, and the direction of induced current is given by Lane's law. So we are going to use Lane's law, okay? So according to Lane's law, the direction of induced current, is such that, okay, it is such that it opposes the decrease in flux, opposes the decrease in flux. Now, okay, to oppose decrease in flux, to oppose the decrease in flux, the induced current, okay, the induced current produces, okay, magnetic field in the same, okay, in the same direction, as the external field. Clear? And what we have, okay, we can see external field, okay, this is external field, this is external field, that is magnetic field, and is perpendicular inward, okay. So the induced current produces magnetic field in the same direction as external field, that is induced current produces magnetic field, okay, it produces magnetic field perpendicular to the plane of the board and directed inward. So we have this. So we now, okay, use right hand rule. Okay, we have magnetic field in inward direction, okay. So what we do is that, okay, the current in square loop MNOP, okay, flows in clockwise direction, because we have this, okay, when we say or look into this figure, let's say I'm redrawing the figure, okay. So we have this, yeah, magnetic field, okay, this is external magnetic field, okay, external magnetic field, and is perpendicular inward, okay, and we have a coil, let's say it is like this, okay. So we have this situation, clear, this is phase 1 and this is phase 2, and I'm labeling it MNOP. So if current flows in clockwise direction, let's say this is the direction of current, okay? This is clockwise, okay? So we have current flowing in this direction, okay? We have current flowing in this direction. So in order to find the direction of magnetic field, okay, when we crawl the fingers of right hand, okay, so as I said earlier, we use right hand rule, okay, we use right hand rule. So when we crawl the finger, when we crawl the fingers of right hand, okay, when you crawl the finger of right hand in the direction of current. So in our case, okay, we have a clockwise, then the stretched thumb gives the direction of magnetic field produced by induced current in the coil. So we have this, okay? So we need to understand this. Clear? Now, next, okay, we are asked to find how long will the current in the loop persist. How long the current in the loop persist. So we have this situation, okay. So I'm redrawing the figure once again, okay. We have this situation. We have this situation. So initially, the coil was at this position, okay. So the coil was at this position. So this is phase 1. This is phase 2. This is phase 1. This is phase 2. So what we find, okay, this distance is 1 meter, that is 100 centimeter. So phase 1, okay, has traveled, okay, this phase has traveled length 80 centimeter, okay. So we have this. Clear? Now when it is completely, so we have this case. So in the question we have when the loop gets out of the field. So this is just, okay, it is about to go out. Go out, okay. So we have this. Now next we have this situation, okay. So we have this situation. Clear? This is 1 and this is 2. So the phase 1, so in this case, phase 1, okay, this phase has traveled this distance. And in this case, phase 1 has traveled this distance. So we have this. Clear? So to find how long the current persists, okay, So what we find is that, okay, we are going to use this relation, speed equals distance by time. So we are going to use this. This is just out, okay? Just out of the field. So from this position to this position, we have change in flux. Okay. So we have change in flux from this position to this position. And let us find this, okay? Induced current flows for time, okay? T1 equals distance, okay? Distance is 80 centimeter for this phase, okay? 80 centimeter by 20 centimeter per second. So this gives us 4 seconds. And next, for this position, okay, we have 100 centimeter by 20 centimeter per second. So this gives us 5 seconds. So what do you find? Induced current flows for time 4 seconds to 5 seconds. So we have this. Now, what we do? Okay, we are asked to plot a graph showing the variation of magnetic flux, okay, as a function of time and induced EMF as a function of time. So let us plot a graph, okay, between magnetic flux and time. So we have time, clear, and we have magnetic flux. So this is magnetic flux, clear. Now, for these two positions, okay, there is no change in flux. So as I said earlier, here we have no change in flux. There is no change in flux. At this condition, or for these two positions, there is no change in flux. Clear? So we have this inside the field. Clear? Now what we do? So let us denote in this way, okay? So we have this. So there is induced current for the time 4 to 5 seconds only. Clear? It means that there is change in flux for time 4 to 5 seconds only. So we need to understand this, okay? So let's say we have this, okay? There is change in flux from 4 to 5 seconds, and we are finding there is decrease in flux, okay? So the flux decreases. And finally, okay, when the loop is completely out, the flux becomes zero. So we have this situation, okay? So this is the nature of the plot between magnetic flux and time. So flux is changing from time 4 seconds to 5 seconds, and we find there is decrease in flux. So we have this, and between 0 to 4 seconds, there is no change in flux. There is no change in flux. Now, next we are asked to plot the graph, okay? Plot the graph between induced EMF, okay, and time. So I'm drawing over here, okay? So we have induced EMF EI, okay? So this is induced EMF. So we have this. Now, we know, okay? We know this. Induced EMF, EI. So I'm writing in this way, okay? This equals minus change in flux d phi by, or we can write in this way. We can write in this way also, okay? D phi by dt. So we can write in this way. Clear? So we have this minus phi 2 minus phi 1 by T2 minus T1. So as I said earlier, so from 4 to 5 seconds, there is change in flux. So I'm writing over here, okay? In between 4 seconds to 5 seconds, there is change in flux. And flux is what? It is decreasing. So this is to be noted. So we have this. And what we find is that, okay, at this time, that is 5 seconds, okay? So let's say this is phi 2 and this is phi 1, okay? So we have this as phi 1. So this is phi 1, okay? And phi 2 is what? 0. So we have this, okay? So we can write in this way, minus 0 minus phi 1, and this will give me, okay, this is T2, this is T2, and this is T1, okay? This is T1. So we have this, okay? 5 minus 4, this gives me 1. So we have this. Clear? So finally we can write induced EMF E equals phi 1. So we are getting this, okay? So I'm writing in this form just to make you understand, okay? So what we find is that, okay, phi 1, okay, it is constant. We can say it is constant in this figure, okay? This is constant. Clear? So for time 4 seconds to 5 seconds, so let me draw over here in this way, 1, 2, 3, 4, 5, and this is 6. Clear? Induced EMF EI equals phi 1, and it is what, okay? Numerically, induced EMF is numerically phi 1, and phi 1, okay, is the flux corresponding to time 4 seconds. So for time 4 to 5 seconds, okay, for time 4 to 5 seconds, EMF is constant, that is phi 1. So this is the plot, okay, of EMF versus time.